It is the derivation of the equation of spherical mirror. This equation is known as equation of spherical mirror, the mathematical equation. It mathematically relates the three distances. The distances are u, distance of object from the lens, v is the resulting image distance, and f is the focal length of the mirror. The mathematical relationship. This equation predicts the characteristics of the image. It will characterize the image formation. This equation precisely determines where an image forms and how big is the image and what kind of image we get, whether it is virtual or real image. That you understand with this equation. So, this equation is applicable for, it is applicable for the designing and construction of optical instruments. There are many optical instruments. Telescope, which is the one we can focus the distant object. Microscope, which is the one we can focus the tiny objects. And cameras, varieties of camera. And also security mirror and the vehicle rear view mirror. There are many optical instruments. We can design and construct these optical mirrors using this equation. That is the importance of this equation. And this equation is applicable for both concave mirror as well as convex mirror. How do we get this equation? To get that equation, we should have a diagram like this. We have drawn many diagrams, but both concave and convex lens. You can use any one of them. I am using this for the derivation of the equation. The mirror is concave mirror, and these are the characteristics of the mirror. P, pole of the mirror, focal point of the mirror, center of curvature, and the object I am taking here beyond C, this object position. If the object is at this position, the image position will be between C and F like this. To find the location, just recall that we do require any two incident rays. I am taking one incident ray parallel to principal axis. After reflection, passing through F. Another incident ray reflecting at point P. After reflection, it is in this direction with an equal angle between the principal axis like this. Incident ray, reflected ray, normal to this. These two angles are same. Where the intercept, the reflected rays gives the position of the image. This is the image formation between C and F. This diagram is useful for the derivation of this equation. In this diagram, see that there is an experimental evidence. The distance PA, distance of object from the lens, PD, distance of image from the lens, we always measure from the point P. These two distances are variable. When the object distance from the lens changes, the resulting image distance also changes. Therefore, these two distances are variable. But the ratio, the distances are PA and PD. PA, PD. But the ratio remains same. Variable, but the ratio remains same. This is of course experimental observation. And one more like that. These distances, PF, this distance is called as focal length of the mirror. And this distance FD. So this distance is variable, but this distance is constant for a mirror. This ratio is also a constant. That is constant but variable, and the ratio is also a constant. That constant is equal to this constant, as these ratios are equal. It has been observed by experiment. These ratios of the distances are equal for any mirror like this, object and the image. We can also prove by mathematical concept or geometrical concept. Experimental observation, of course, we can prove by mathematical, that is using the geometry, knowledge of geometry. Let us go for proving this equation. This is what the diagram you have. In this diagram, I am taking the triangles, two triangles. This triangle with the object, and this triangle with the image. This triangle is ABP, this triangle is PDG. These two triangles are similar triangles because two angles are equal. Two angles of both the triangles are equal. This angle is 90 degree, this angle is 90 degree. These two angles are equal. And more one set of angles. This angle of this triangle, this angle of this triangle are also equal because angle of incident, angle of reflection. So if two angles are equal, then such triangles are called as similar triangles. These two are similar triangles. The condition for the similar triangle is that the ratios of the sides, corresponding sides. This is the corresponding sides. I am taking this as AB. This side of one triangle, this side of another triangle, corresponding sides. The ratio of the corresponding side. This ratio of corresponding side and other corresponding sides, that is PA. I am taking this side as the one side and the corresponding side of other triangle as PD. The ratio of these sides, this is called as ratio. These ratios are also equal. That is, ratios of the corresponding sides are equal. That is what is applicable for all similar triangles. So we can have this equation from these two triangles which are similar. That is geometry, knowledge of geometry. This one equation you get. In the same diagram, you have two more triangles which are similar triangles. This is one more triangle. That is P, that is EP. This is, of course, curvature is there. We can approximately assume that the curvature is almost a straight line like this. This straight line length is equal to this length, almost. So we can make some approximation. This curve, very slight curvature is there, is equal to this straight line BP. This is one triangle. This is another triangle. This is another triangle. These two triangles are similar triangles. Since the angle is 90 degree, this angle is 90 degree. And in this triangle, this angle equals this angle because they are opposite angles. This is angle of this triangle, angle of this triangle. So two angles are equal. When these two angles are equal, these two triangles are similar triangles. Apply the same concept. The ratio of the corresponding sides are also equal. The corresponding sides I am taking this side divided by this side, and this side divided by this side. These ratios are equal. So this is what we get from these two set of triangles. And we are making a approximation here, straight line, then EB is almost equals to AB. This length is equal to AB. So replace EB by AB using this. We get this equation. The equation 2, we get it from these two triangles. Equation we get, that is 1, we get it from these two triangles. Compare these two equations. Left hand sides are equal. Left hand sides are equal. Then the right hand sides must be equal. So you can write this, right hand side is equal to right hand side. So we can have this equation with this knowledge. This equation is similar to this equation. Look at that, this is how we have proved that it is the equation what is observed experimentally same as theoretically. It is proved by geometry. So with this equation, finally, the last one is just a substitution for these distances. And you know distances you are measuring. All from the point C using sign convention. As you know, sign convention means if you measure any distance from the point P in the direction opposite to incident ray, takes negative sign. And if you measure the distances in the direction same as the incident ray, takes positive sign. So all these distances what we measure from it is always in the direction opposite to incident ray. In this day we are measuring. This distance is minus u with sign. This distance is minus v. This distance is f minus f because of sign convention. And this distance df. Let us write this df in the form of standard. That is dp minus what is that pf. This distance minus this distance is distance. PD is v minus v. Sign convention. Minus is there minus. PF is f minus f. Simplify. This becomes plus f minus v. Now we have all these distances with sign convention. Substitute them into the equation 3 and simplify what we get. Equation substitution, that is minus u minus v. Minus f divided by df is f minus v. And simplify the equation. Minus is there, minus cancel with this. We can cancel this minus, taking out minus here, common factor, plus and interchange v minus f. And this equation requires manipulation, that is all. Interchange numerator and denominator. If you interchange the left hand side, right hand side, so nothing will change. Interchange numerator, denominator. numerator as denominator. It will change. Simplify the right hand side, dividing this v by f minus f by f minus 1. And the final is divide the whole equation throughout by v. This term divide by v, 1 by u. This term divide by v, 1 by f. This term divide by v, 1 by v. The same equation, take this onto the same side. 1 by f one side, these two on the same side. It becomes plus. So final equation is 1 by f equals 1 by u plus 1 by v. This equation is the equation of spherical mirror. This is how we can derive the spherical equation using the diagram, symmetrical diagram. We can use any one of the diagrams. We will draw the equation that is diagrams, many diagrams for both concave mirror and convex mirror. We can get this equation. But the concept is that this is holds good for any mirror, whether concave or convex. The ratio remains constant as these two are variables, distances are variable according to this experimental observation. With this, you have completed the derivation of the equation of spherical mirror. Thank you.